Okay, let's go ahead and look at 4 examples here that involve limits of trigonometric functions. So the first one that we have here is a pretty straightforward limit. You'll notice that we're just evaluating the limit of the sine of x as x approaches pi over 2. Now, for whatever reason, whenever we start throwing in pi's or some other variable down here, it tends to confuse people. But this is just a number. Pi over 2, remember pi is just 3.14 divided by 2, so it's just a number. Think of it as x is going to 1 point something, whatever that might be. Okay, so remember my go-to method. My go-to method is just see if you can plug this in for x. So if I plug in pi over 2 in for x, I get the sine of pi over 2. And what is the sine of pi over 2? Well, the sine of pi over 2 is just 1. So this limit is just 1. Okay, I can actually go to my calculator and look at the graph of this thing. Here's the sine of x right here. Now just some calculator tips here. It's hard for me to imagine where pi over 2 is on this line unless I come into my window and I specify exactly a scale that will help me to see where pi over 2 actually is. So I don't need to look too far to the right. So I'm actually going to enter in 2 pi for my x max. And since pi over 2 is to the right of 0, I don't know why that didn't show up. Since, I'm sorry, I didn't want that as my minimum, I wanted it as my maximum. So let's start over here. Here we go. My x max I want to be 2 pi. And as I keep changing my window, you can see my graph updating down here. Now here's what's going to allow us to figure out where pi over 2 is. I'm going to actually let my scale count by pi over 4. In other words, 0, pi over 4, the next one would be pi over 2. Okay, and this is a lot of wasted white space up here, so I don't need to look too high and too low. So I'm going to look up or down to -2 and up to +2. And that should take care of it for me. Let's go ahead and look at the graph of this now. Okay, so here we go. Here's my scale. This is 0, pi over 4. Here's pi over 2 right here on this tick mark. This is +1. This is +2. So as x gets close to pi over 2, we can see that the sine function is getting close to 1. And it turns out that if we jump to the right of pi over 2, it does the same thing. Okay, so graphically, it confirms what we got analytically. Jumping back to our second example. Another pretty basic example in the sense that we can go ahead and use our direct substitution technique here. X is approaching 2, so I could just plug that 2 in right here. And I get the cosine of, I'm going to call that 2 pi. I just rearranged where the x actually is. 2 pi over 3. Okay, now I just need to evaluate what the cosine of 2 pi over 3 is. Well, where is 2 pi over 3? 2 pi over 3, another way to say 2 pi over 3 is 4 pi over 6. And where is 4 pi over 6? Well, here's 1 pi over 6. Here's 2 pi over 6. Here's 3 pi over 6. Here's 4 pi over 6. I just counted to it. Okay, if I draw a little triangle here, we know that the cosine is always your adjacent leg. So there's your cosine right there, assuming that this hypotenuse is 1. And that short leg, if you know your unit circle, that short leg is always going to be 1/2. Okay? And since it's in the second quadrant, we know that it's negative. Okay, so this limit is -1/2. Okay, so we had a little bit of unit circle review for you there in case you get stuck with those. Okay, the third example if we try to use direct substitution in this example, look what happens. We plug 0 in the numerator and we get back 0. And we plug 0 in the denominator and we get back 0. Not good. This is our indeterminate form, and we know from past examples that anytime you get a limit where you're trying to take the limit of something that's in indeterminate form, if you plug your value in, that you have to manipulate the function to get it to something more recognizable that you can use direct substitution in. Well, let's look at this very carefully. This function here actually looks a lot like this guy right here. Okay, and we know what that limit is when x approaches 0. It's 1. So it'd be really nice if I could manipulate my new function so that I somehow can see this. Okay, so scrolling back down here, I'm actually going to take the sine of x over x, and I'm going to just rewrite it slightly differently. Okay, one thing you'll notice is that we're dividing the sine of x over x by 5. So that would be the same thing as multiplying the sine of x over x by 1/5. So this looks really familiar now. Okay, now all I need to do is I need to I need to use some properties of limits. And one property that I'm going to be using in this example is, suppose I have a limit of the product of two functions. I'm letting x just approach some random c here, and maybe I have two functions. Okay, so the limit of the product of these two functions, I don't know what these functions are. They could be anything we want them to be. In this case right here, I have a constant function, and I have this other function in terms of x. Okay, well, the property says, and we won't prove this right now, we'll just kind of take it for truth. This limit, turns out, you can break up into a product of limits. In other words, I can look at the limit of the first function and then multiply it. I'm going to run out of room here, aren't I? Let's rewrite this down here. We get the limit as x goes to c of f of x times the limit as x goes to c of g of x. Okay? In other words, the limit of a product of two functions is the exact same thing if I take the product of the limit of those two functions independently. Okay, well, that's exactly what I'm going to do here. I'm going to look at the limit as x goes to 0 of 1/5. I'm going to multiply that by the limit as x goes to 0 of the sine of x over x. Okay, well, what do we have here? We have the limit as x goes to 0 of a constant. What's the limit as x goes to anything of a constant? Think about what a constant is. The function 1/5. The function 1/5 is just a horizontal line. If this is 1, then 1/5 is right in here somewhere. Okay, it's just a horizontal line. So everywhere along this line is the y value is 1/5. So as we get close to 0, either from the left or from the right, we're always going to be at 1/5. Okay, so really, this limit right here is just 1/5. And we're going to multiply that limit by this limit. Well, what's that limit? Well, we did that up above. Okay, we know already that the limit as x goes to 0 of the sine of x over x is just 1. Okay, so we don't have to do anything other than just call that 1. 1/5 times 1 is just 1/5. And we're done. Okay, so this was an example of where we actually used our knowledge of a previous limit and we broke down our function into the product of two other functions and evaluated those limits independently. Okay, the last example here is going to be done very similar. And the technique I'm using here, first of all, if you can't use direct substitution and you have some sines and cosines involved, I always try to look for these two functions embedded in my limit statement somewhere. Okay, so if you look carefully at this thing, I have a sine of x up top. I even have a 1 minus cosine x. And good thing we have an x squared down below. Okay, so let's try to rewrite this function in such a way that we have maybe a couple of different functions that we actually know the limit of. Okay, so I'm going to recognize that this down here, I'm just going to take that 2x squared and I'm going to rewrite him as 2 times x times x. Okay, so think of 2x squared that way. And if I do that, then one of the x's I can put underneath the sign times 1 minus cosine of x over another x, and then I have to deal with that too, and we could just call him 1/2. Now if you don't believe me that we can actually do this, just go ahead and multiply these fractions together. Okay, if I multiply my numerators across, I simply get this, and if I multiply my denominators, I get 2x squared. Okay, well this looks pretty familiar. We know the limit of this, we know the limit of this, and the limit of a constant is simply that constant. Okay, so just to be thorough, let's go ahead and rewrite the limit statement here. I don't know that I would do this every single time. You'll get to a point where you can just kind of say, well, that's 1, that's 0, and that's 1/2, so the whole thing will be 0. But let's write it out to be thorough. Whoops, not sine, but sine of x over x times the limit as x goes to 0 of our next function times the limit of this constant, which is just 1/2. Okay, so now we can just go ahead and evaluate this. This is 1 times, this right here is 0, times, and this right here is just 1/2. Okay, crunching that, this 0 just kind of wipes everybody out to begin with. So this limit, the limit as x goes to 0 of the sine of x times 1 minus cosine x over 2x squared is 0. And you could check that on your calculator. You can look at a graph. You can look at a table to confirm that. Okay, so again, when I have a trig function and I can't use direct substitution, I try to look for these limits within my function that I might be able to pull out and evaluate them independently. I hope that made sense. We'll look at some more examples in the next video.